simply means smaller amount of search. In general, it's not, it's not a directly probable proposition, but in general, HFN being larger means it's going to do less search. This is why the dream, if I came up with two heuristics which are admissible from orthogonal considerations on abstracting the space, it would be so cool if I can add them up. Then because we know that they're both positive numbers, so if you add them up, the new heuristic will be bigger than the previous heuristics. And so it definitely will do less search. I don't know. Okay. It's going to do less search. And so, so that's why we are interested in finding such heuristics, but unless some pretty problem-specific tight constraints are satisfied, you will never be that lucky. In general, you can't just add up the heuristics and hope that the new heuristic will be easy. It will do less search, but it will not be admissible. Not guaranteed, yes.
Can you show an example of that? I'm not quite seeing it.
Okay. Okay, I will show you that example in a second. In fact, there is a nice picture that's coming up. But so today, the agenda is improve your intuitions and admissibility, which is pretty much what we are doing till now. Okay, and I'll show one more very interesting slide. Understand A-star search admissibility proof. That also I want you to understand. And then understand how admissible heuristics come from abstractions. I gave you one example of you all being, I'm doing a disappearing act for on you. So that I can then do a planar search. Okay. So first we understand that they come from abstractions, and I've showed you the path planning example. And I want to also get you, before we are done, that the abstraction, if the abstraction is just a little bit easier than the original problem, that means it's a close abstraction. It's very close to reality with just a little few features removed. Okay? In that case, the abstract problem would be just as hard as the original problem, almost. But the cost in the abstract problem will be much closer to the real world cost. So it turns out that there is actually going to be a trade-off between the cost of computing a heuristic and how good it is in actually reducing the search in general. And that's something that we will talk a little bit about. Then we'll talk about pathmax correction and IDA stuff. So that's basically the agenda. But since you wanted to, let me actually do this. If you wanted to see the examples, let's just go quickly. Okay. There you go. Okay. This one, I'm not going to play with Socrates because it takes too long. I'll ask you to raise your hands. Again, this is to get your heuristic intuitions up. Okay? It's a bunch of questions. Okay? So there is some problem, abstract problem, for which I am plotting the nodes here. Node 1, node 2, etc. And the heuristic value here. Okay? And this turns out to be H star for this problem. That's a perfect heuristic function. Remember, it has to be a function. It's actually a discrete function. I just sort of connected all the dots. It's not a continuous function. Okay? Because you only need the value for heuristics at each search node, and there are only discrete number of search nodes. Okay? So keep this in mind, and also, as we go forward, ignore just this very right end, because things can be slightly off at the extreme right end. Just look at the overall topology of this heuristic. First of all, first a question. So, does this problem have a solution? Raise your hands if you think there is a solution for this problem. There is no solution because H star n is not 0 anyway. This is just sanity check, right? If in fact it's a real heuristic, then it should have been 0 at some percentage. But be that as it may, let's just assume this is the perfect heuristic. So I'm going to show you some heuristics. H1, admissible or not? Quickly.
Yes.
Okay. H5?
No.
Okay. H4?
No.
But look, so many places. That's what you don't want to fall for. You see what I'm saying? This guy is just inadmissible in these few nodes. But there is no such thing. There is no such thing as I'm a little dead. Right? And similarly, there is no such thing as a heuristic is mostly admissible. It's either admissible or not. If it is actually not a lower bound, even at a single node, it's not admissible. That's what I was telling you. Okay. How about this? H2?
Yes.
How about H3?
Depends on how you draw it.
Now this is H3.
Yes.
Does it cross it?
Okay. How about max of H2, H3? Okay? Because remember, max essentially takes the envelope of the two curves. That's what you wind up doing. So max is basically like this. Notice that max has to be admissible because it won't be bigger than the biggest heuristic. And since both heuristics are always below H star, max of H1, H2 is going to be better. So remember, I was showing you two heuristics that came from two very different directions, and you want to somehow use both of them. You would love to add them, that won't work. But you can certainly do max of both of them. It turns out you can also do min of the two heuristics. So imagine I wrote the min of those two heuristics. Would it be admissible?
Yes.
Would you use it instead of either of the heuristics?
No.
If you even thought for a few microseconds that, yeah, that looks like a pretty complicated min expression, let me use it, you are totally wrong. Okay, that's like basically saying I don't want to use the knowledge I have. Min is useless. Max is pretty useful. In fact, max is a way people wind up getting admissible heuristics by combining multiple heuristics, where the heuristics come from basically different types of abstraction. And then, let's see, there is one more. Okay, so with respect to this, if I were to, for example, add H3 and H2, okay, H3 and H2, at this point, you can see, even though I didn't show the picture, at this point, at this node, H3 is this much, H2 is also this much. If I add both of them, I will be above the red line. Whoever asked the question as to why is H2 plus H3 not going to be admissible, that's your proof. I just need to show you that at least there can be one node where if you just add them, you will be, the addition heuristic can be higher than the perfect cost. Perfect heuristic. That's why adding doesn't help. Okay, but clearly adding will make the heuristic come even above this. By the way, in all these heuristics, which one do you think will, ignore the red, of all these heuristics, which one do you think for sure will do much less search than others? H5. In fact, the way to do the least amount of search is to put H5 to be at plus infinity. Every node, you'll get done very fast. I mean, you'll get done. It's not optimal way of doing it. Nobody ever said that you're getting optimal solution. But you'll get done very fast. There was a yes.
So if you have like maybe something similar to H5 for your problem, like it's an overestimate, is that like completely useless data? Like for example, maybe there's some problem where you can't get an underestimate always, and like,
okay,
is it completely useless?
Okay. So remember, I already asked you to write down one thing in the class today. That correctness is local, optimality is global, and then you should put like a big box around it. Right below that comes the second commandment. Okay, the second commandment is the difference between a computer scientist and a hacker. Okay, a hacker or a programmer given a problem comes up with a program. If it's working, it's working. I don't know, don't care whether it's optimal. Computer scientist, on the other hand, tries to see under what conditions the algorithm would be optimal. What conditions can you actually prove properties of the algorithm? Having proven it, they want to live too. So in some cases, if it's too hard to find an admissible heuristic, you just use the heuristic you have. The difference is computer scientists know that they're screwing around when they actually take inadmissible heuristic. Hackers didn't know, didn't care. That's the only reason you're doing a CS program as against doing DeVries or whatever is still available to do some hacking. Okay, so it's a very, very good point. In fact, in many cases, if in fact you don't need to ensure optimality, then people just wind up using inadmissible heuristics anyway. But the difference is they are doing it with full knowledge that they are screwing around. They actually are not going to get optimal. And if you don't see the difference between both these lifestyles, then you should save your tuition dollars and just do some hacking course. Okay? So in reality, you understand the properties of algorithms, and where in fact you can easily be optimal, you should be. Where it is impossible to be optimal because you can't get admissible heuristics, you find whatever is the reasonable one that you take. The whole thing of this is, given a problem, start typing the program. Don't do that. Think a little bit. Okay? But it's a really good question. In fact, if you look at the literature on A-star search, in actual practice, people do use sometimes heuristics that are known to be inadmissible. But they'll say, look, we understand. We understand it's something inadmissible, and then we understand that it's not. In fact, one of the other interesting things that a true computer scientist will do is to come up with heuristics that are not admissible, but then come up with a proof saying, if you use this heuristic to come up with a solution, it won't be more than this much away from optimum, no matter what the problem is. These are approximation guarantees. Okay? Sometimes you can do that, not always. In general, it's not very easy to get that. Okay? In fact, basically, in general, in practice, people do sometimes, in fact, many times use inadmissible heuristics. The only case where they cannot at all use is they're actually trying to say, I am going to find an optimal solution to this problem. In that case, if they don't use admissible heuristic and if they find a solution, there's no way of checking whether it's optimal without having to do everything later. In those cases, they must use it. If I'm just trying to get to John, if I'm taking a slightly suboptimal path, it's not the end of the world. Okay? That's a very, very good question. Please write this down, and keep it in the back of your mind, because that's really the difference between CS and IT. Yes?
So if assuming I'm using H5 heuristic to find a solution, am I guaranteed to find a solution, or may not be optimal?
No, again, remember, in fact, the moment you're not admissible, you're not even guaranteed to find a solution. Like, for example, if there is a solution, you may still not find it. Okay? So imagine I give you a search tree which has goal nodes at 15th level, 25th level, 89th level. Okay? An inadmissible heuristic might, instead of finding the 15th level, might find 25th and 89th level, or it might just terminate saying, to heck with it, I'm done. That's what that kid who basically said, okay, I look at this paper, I'm just going to go home. There are actually easy questions. Sometimes I give easy questions. And they could have seen the 15th page of the exam and found that there are easy questions. They didn't even bother. That's what I'm saying. So, once you are not admissible, depending on, if you're looking at all possible cases, there could be cases where in fact you would not even be complete. Completeness basically means if there is a solution, you will find a solution and terminate. All you do is just terminate. Yes?
So when you are saying the searches first, basically it is like traversing the nodes, not actually finding the solution.
What do you say?
When you are saying like the searches first in case of like inadmissible heuristic.
Search, okay, so the cost of search is exactly measured in terms of the number of node expansions you do. If you look at the search template I gave, there is a place where the search algorithm calls, give me all your children nodes. So given a node, finding its children nodes is considered search expansion, node expansion. Depending on the problem, the node expansion can be very, very costly. So in general, when I talk about the complexity of a search, I just talk about the number of nodes expanded. Not the number of nodes generated, but the number of nodes expanded. On the other hand, if I'm talking about the space complexity, which is how much space does the search take, I'm only talking about the size of the open list. Because if you generate a lot of open nodes and then a lot of nodes and they're all hanging around in this queue, that queue takes some space. So space is just in terms of the open list size. Time is just in terms of the number of expansions. Okay? Yes?
Just to go back to the approximation again, does that only apply to the invisible or something like approximation?
No, I mean, you don't need approximation at all for admissibility. If you are admissible, then you are just optimal. Okay. Only if you are not admissible, you are no longer guaranteed to be optimal. The question is, how far from optimal can you be? For some very specific problems, people have proven theorems saying if you use this inadmissible heuristic, then you would not be. So, as an example, one of the favorite problems that we talk about at some point of time is what's called Block's world. Okay, Block's world is there is a bunch of named blocks, on the table. Okay, in some configuration, let's say A is on top of B, and C is on the bottom, and C is on the table, and D is on top of C. Okay, given this configuration, I want you to get these blocks into a different configuration. Let's say put A, B, C, D. You see what I'm saying? So there is an initial configuration for the blocks. I want you to get them to a final configuration. Okay, that's Block's work. Very simple. You keep hearing about it as like a toy problem in many situations. An interesting heuristic for Block's world, it turns out, is put everything on the table and then build the stack in the order you want. Do you understand what I just said? So if A is on top of B, C is on top of D, put A on the table 2, C is on the table 2. Now everything is on the table. Now you want A, B, C, D, so you just know that you have to put B and then put C on top, then put B on top, and then put A on top. You're done. That's a way of building the stack. Clearly it's not optimal. Right? Clearly not it's optimal. As an example, if I had a stack which has B, C, D, and A is on the table, and if I wanted A, B, C, D, all I needed to do was to put A on top of B. But this heuristic will basically undo the whole thing, put it all on the table, and then reconfigure the stack. Clearly inadmissible. But it turns out that you can prove that the length of the solution in terms of the number of stacks and pickups, etc. that you do will not be more than twice the length of the optimal solution. Will not be more than twice the length of the optimal solution. That's the kind of proofs you can prove. That proof only works for that Block's world, nothing else. Yes?
So is a guaranteed solution and admissibility, are they mutually exclusive? Can you have an inadmissible heuristic and still guarantee solution?
Guaranteed means it's basically complete. It has a completeness. That means, so for example, pretty much any, so for example, depth first search is clearly inadmissible. Okay, and yet, on a fixed length, in a fixed depth tree, depth first search will always complete. You just find probably a solution that might be deeper than is needed. So that is possible. Any other questions? So again, what I'm doing is I'm hoping that you actually did look at the A-star search lectures before coming. For those of you, it's like the reduced Shakespeare company. They say that the more you know the original, the funnier the reduced Shakespeare company is. So the more you have actually followed the lectures before coming, the more of this nuanced discussion that will help. Otherwise, you'll catch up on your sleep. because this is actually second order nuance discussion, and this is the way you really understand the material. Yes?
How do you find an H star?
What?
How do you find or decide that this is going to be H star?
Okay, so that's basically, there is no such thing. If I know the H star, then I don't need to solve the problem.
Then
Okay, so any problem for which H star can be computed in polynomial time. So here is the interesting thing. So there is this other idea called weak methods. Weak methods. A weak method is one that applies to any problem, but is not necessarily the best solution to that problem. Search is a great weak method. Any problem can be solved as a search problem. You don't believe me. You know sorting, right? Can you write sorting as a search problem? Yes. Okay. Now, if you write sorting as a search problem, and in fact, suppose you want to count the number of swaps you did, every time you shift the number from one place to another place, that's actually a shift. So if you're counting the number of swaps you did to get from any arbitrary configuration to a sorted configuration, you can write that as a search problem. For that problem, H star would be polynomial, because you can always go back to 310, and for the H heuristic, you can just use double sort or quick sort as the exact number of moves that will be needed. So anytime you can compute H star as a polynomial time, then in fact the original problem should have been run as a search problem at all. You see what I'm saying? Because it's a weak method, search will always raise its hand saying, yeah, use me. But you don't use it if in fact H star is actually computable with polynomial. It's most useful for problems where H star cannot actually be computed any more easily. In that case, you're actually using these abstractions. Okay. Let me show you this other one. Yeah. So I assume that you've seen this in one of the lectures yesterday, depending on how many you actually went through. But so this is a classic, a slightly different version of the same path planning example. Okay, and this is actually more realistic. So here is I and here is G. Okay, right? And a robot is trying to go from this node to this node, and it's just trying to do some, actual path planning. Robots use these kinds of algorithms. Okay. So the question, of course, is these obstacles are all irregularly shaped, right? So now, if I want to find the optimal path from I to G, it requires search. Now, if I'm computing the heuristics, right, there are multiple ways I can compute the heuristics. Okay, one is, of course, assume that the obstacles disappear, which is the first idea I gave. If the obstacles disappeared, then the shortest cost path from I to G is just a straight line. Yes? Now, is there going to be such a path that is actually doable? Of course not. In fact, if you connect I to G, it's actually going through the obstacle. In real world, you can't go through the obstacle, which means this heuristic was way too optimistic. People who are way too optimistic might spend a lot more time trying to get to the solution, but eventually they'll get to the solution. What's the most, we kept talking about the most pessimistic heuristic, right, which is basically H equal to infinity. What's the most optimistic heuristic? Yeah, so you don't even need this class. There's one side infinity, other side should be minus infinity unless you don't allow minus, in which case it's 0. Right? Indeed, it is the case that the most optimistic heuristic is H equal to 0. Do you know of any search that uses such an optimistic heuristic? Breadth first search, uniform cost search. They're all using essentially optimistic heuristic. But they're cluelessly optimistic. There's a difference between being cluelessly optimistic and overly pessimistic and being just the right level of optimism, informed optimism. Good admissible heuristics are trying to get to that midpoint, the informed optimism. Okay, so anyway, this one would be actually a solution, a principal heuristic, but it's not going to be very good because it's likely to, the search algorithm probably assumes that this is the path, and so it will find the hard way that those things don't work and it will have to expand other nodes. So it's better than saying h equal to 0, and yet it's not much better. A different version is this. I inscribe circuits on, into each of these irregular obstacles. You see what I'm saying? Now if I do this, clearly, again, circles are always easier to deal with. Right? In fact, one of the things that you can do is you can just think in terms of tangents to the circles, and the optimal path will involve going via the tangents from right to G. You see what I'm saying? Now, once again, the problem is this is going to be more informed than this. This is an abstraction that is closer to reality. It's not assuming that abstractions completely disappear. You see what I'm saying? So it's a closer to reality abstraction. So computing even the heuristic in this case will be costlier than just finding the straight line distance. But that heuristic is going to be better. In the sense it's both admissible and it's going to be at least it's equal to or higher than the straight line distance. I hope you understand this. Now why would you do this when you can do this? In some sense, when you came from here to here, in fact, before this there is one more, which is basically don't even ask Euclid, assume everything equal to 0, all H's are equal to 0. That's like the most clueless optimism. Next comes Euclidean optimism. Next comes this. As you go down like this, the cost of computing the heuristic is increasing. And yet, the amount of nodes that you are actually expanding is hopefully reducing. So these two costs, one is increasing, one is reducing. So the total cost is going to be the sum of those two. And it's important to figure out where that happens. You don't know upfront. Okay? Let me show that picture in a minute, but so this is a circular abstraction. This is a polygonal abstraction. Polygonal abstraction is even better than a circular abstraction. It almost gets the entire shape of the obstacle. But then computing this heuristic is going to be costlier than even this. But this heuristic cost is going to be even more informed than this. I'm sorry, right? Even more informed than this. The other is, the final one is brute force optimal heuristic. Where you say, I want to prove that I can compute H star. So what I'll do, I'll not do any abstraction at all. I'll take the real problem. And for every node where I need to compute H value, I will call another search here, right there. And it will find me, if I set H equal to 0, it will find the optimal solution. You see what I'm saying? In fact, so when I'm doing this, I'm basically doing a full search where at any node I know the G value because I know how far I have traveled. For the H value, I will actually do the full search. This secondary search can use any of these heuristics. As long as they're admissible, it will find the optimal solution. And that optimal path will be H star. Clearly, by this time you have jumped the shark because you are essentially solving the problem many, many times instead of solving the original problem. And so there, the cost of computation of the heuristic is so high that even though the number of nodes expanded has become very low, the total is still quite bad. And what we are saying is, let's just this picture. This is a very, very important picture to keep in mind. And in many interesting issues, many interesting algorithms in the world, this sort of trade-offs happen. Okay, so here, essentially, I am drawing the x-axis as the various heuristics. listed from least informed and cheapest to compute to the most informed and the costliest to compute. They're all admissible. So, the amount of, when you complete the search, right, you see at the clock time. Certain amount of that clock time has been spent just computing the heuristic. Even if it was just computing the Euclidean distance, that takes a little time. You have to take x1 minus x2 square plus y1 minus y2 square, the whole thing square root. Obviously negligible amount of time, but it does take some time. So they take the amount of time you spent total in computing the heuristics at every node, and the amount of time you spent in computing the expansions. Okay? Now, those are the two parts of the search cost. Those are the two parts of the search cost. You add them up, you get the full search cost. So, as you go from H0 to H star, the heuristic computation part of your search is increasing. Okay? And at the same time, you more or less assume, I mean, these are obviously abstract curves, these are not really for any specific problem. At the same time, the amount of time you spend expanding the nodes is going to be reduced. The question is, what are you trying to optimize? You're trying to optimize the sum of these two curves at any point. And the sum would look like that two curve. So, what you want to know is, what is this point correspond to in the heuristic space? Do you see what I'm saying? Obviously, this is not known, but you need to understand that the too cheap to be good, too cheap to be true kind of a heuristic, as well as way too costly heuristics are probably likely to be decided. Somewhere in between is likely to give you total cost improvement. And in fact, this is one of the things you will be doing in part 2 of the project 1, where we ask you to come up with heuristics. And there are many different heuristics that you can come up with for a Pac-Man problem, depending on what you abstract and what you don't. And one of the interesting questions is that, if you just want to get done with the project, you just find the cheapest, simplest to think of heuristic. It will be somewhere around this area. And you will be done. But then your total solution cost will be there. And so to make your life miserable, we basically see how, and we have some idea as to what are the good heuristics, and we'll see whether or not you're able to get done within certain total amount of time. If you don't get done, then in essence, you'll have to go in this direction, coming up with better and better abstractions, closer to reality. Remember that anybody could have come up with this abstraction. Cats do. They close their eyes and the world disappears. Right? But we are not cats, so we should be able to come up with better abstractions. You see what I'm saying? So that's part of the part 2 of the project that you will actually wind up doing. So there were several raised hands. Yes?
So just to understand this more, let's just say for this problem, we want to come up with the